now. Let's try that again. Okay, so for the final, I want you to see the connection between a line and a curve, x, y intercept, x, y intercepts. Why are we factoring? Why do we care? Why are we bothering to factor? Well, generally, we want to do it so that we can sort these x's out by themselves. So what is it that we more generally have to know? Well, we have to know that what happens is it's going to take a lot of practice to learn how to factor. You just have to do the homework. But with regards to the next more complicated thing is that you would have something like in the neighborhood of, let's say, so let's suppose that you had a y equals, and now we have x, notice that x squared. And then in this case, let's say I have 2x minus 5. Now, you can see that factors of 5 are what? Whole numbers. 5 is a prime number, so how can you write it only as 1 times what? 1 times 5, right? So you can see 1 times 5, if you subtract 1 from 5, you don't get 2, do you? So, how do I solve it? We did it last time. How do I solve it if it's not nice? Okay, this is alright, right? When x is equal to 0, you can see that this is still going to be minus 5. You see? That's still the y-intercept. But the fundamental theorem of algebra tells us what? That we have to set y twice equal to 0. And then we're going to have 2 solutions for that. So, does anybody remember the technique now that we used in the case of it not being nice to us? What's it called? We weren't here. We don't know. You were here, you were here, you were here. You were here? Were you here last time?
On Monday?
Yeah. Oh, okay. Unless you listen to my lecture. Okay. Anyhow, online. What? Any good? You remember? What did we learn? What technique did we learn last time? Blank. It's called completing the square. You don't remember hearing that in your lifetime? You remember the word completing the square? You see, I found it. I think it was always there. Completing the square. Does anybody remember talking about, do you remember that hearing that term? You do? Oh, okay. All right. But you remember hearing it kind of vaguely before, it was kind of something in class that you heard one time. Okay, this is how you do it. This is how you do it. You take the constant and you bring it over here. So I'm going to add 5 to both sides, yes? Okay? Okay, now, you always take the middle term, this guy, the 2, the coefficient, not the variable, the 2, and you do what? You divide it by 2. Can somebody tell me what 2 divided by 2 is? Ooh, good. And you take that answer, which is 1, and you square it. And because you don't want to change the thing, you're going to have to add a 1 squared, which is 1, correct? Let me see, yeah. So you see that this is equal to 6, correct? And this, because we forced it to be this way, is a complete square. Look, what's it mean when you have a plus sign here? You duplicate the sign in front. So that means plus, plus. And you have to have a 1 and a 1, don't you? Otherwise, you'll never get 1 squared back, and you have to have an x and an x. If you try that, you'll see that x times x is 2 copies of x. Plus 1x here, plus another x will add up to 2x. And 1 times 1. Do you see that? Right? You don't see it? You want me to do it? X times x is what? X times x is what? X squared. What's x times 1? It's x, isn't it? What's 1 times x? It's x, isn't it? And what's 1 times 1? Well, you can write it as 1 squared, it doesn't matter, yes? Isn't that equal to x squared plus 2x plus 1 squared? It did get back to it. And it has to by design because we took this middle term, divided it by 2. This will always work. This is what complete with square is. Now, do you see I have 2 copies of one of these? So I can write that like this. Look, I'm going to change the order. I'm going to put the plus 1 here. I'm going to square it, and that equals 2, 6. What am I trying to solve for?
X.
X, right? It goes here and here. Okay, now, this is, you probably missed this too. We went over square roots. It turns out the square root is equal to what? The square root is equal to, can be written as x to the 1/2 power. Yes? So, in general, if you don't see it, there is a 2 in there, but it's so common we don't put it. So how about the cube root of x? That can be written as x raised to the 1/3 power. And so on. Till you have the nth root of x, which is going to be equal to x to the 1 over n. Do you see that or not? Why do I care? Because if you take, here's a rule, if you take the square root of a square, look at this, for example. Let's say, all right, what are the answers for x? Well, x is equal to 3, right? 3 squared is 9, correct? The square root of 9 is 3, yeah? But x can also equal to minus 3 because it's squared. Makes it positive 9 again, right? So what happens? There are 2 solutions. So what I'm trying to tell you is anytime you square root this, then you have to square root this, but there'll be 2 solutions always, plus minus. Right? Because I told you an example over here. There's going to be x minus 3, and there's going to be equal to x to a 3. Okay? Now, what does this mean here? This means instead of writing like that, we can write it as what? Instead of this symbol, we can write it as what? This thing raised to the what power? We can rewrite the square root as what? Half power. So, we can write that as x plus 1, correct? Squared. And this red thing here can be written as the half power. And this is still going to be equal to plus and minus the square root of 6. Okay, now, what happens when we have a power to the power? Do we multiply or do we add? Multiply. When you have, x3 quantity, let's say for example, squared, you're going to have, what, 2 packages of cha-ching, right? But you can see that that's going to be 3 copies and 3 copies for a total of 6 copies, true? True? The shortcut is just 2 times 3. So I'm asking you, what is a half times 2? Oops. 1. Guess what? We got rid of it. So now we just have x plus 1 equals plus and minus the square root of 6. You see? You have to know your square roots. You have to know how to factor. You're in good shape if you can follow it along. there any questions? Is it too easy? You want to solve some on the board?
So what would you do if you had a really long square root, like the square root of 6? The decimal goes on for a really long time.
Square root of 6?
Yeah.
What do you mean? The long one. What do you mean by the long?
I mean, there are a lot of numbers after the decimal.
Oh.
Like.
Oh, we're just gonna estimate. Like right here, I'm not done, right? So I'm gonna subtract 1, right? So I have my x-intercepts will be equal to minus 1 plus and minus the square root of 6. So this represents two solutions, right? One's going to be, go the high road is minus 1 plus the square root of 6. And the other x-intercept is going to be minus 1 minus the square root of 6. Guess what goes in here? Yes, minus 1 plus the square root of 6. And minus 1 minus the square root of 6. You see it? Okay, now she's asking, well, how do we handle the decimals when graphing? Well, I mean, the decimals go forever. When you graph it, you're going to eventually make a guess, right? So let's take a look at the square root of 6. And let's look at that. Well, we don't know exactly what it is, but we do know what the square root of 9 is, don't we? And we do know what the square root of 4 is, don't we? So we know that the square root of 6, what? Is 6 closer to 9 or 4? It's closer to 4, so I don't know, you can try it, but it's probably something like 2.4, something forever and ever, right?
Yeah.
So all I really care about, and so far as graphing, is I'm looking at my solutions as roughly, squiggle means roughly, let's say 2.4 minus 1. So it's 1.4, do you see that? And this one's minus, so you're going to have minus 3.4. You see it? Or not? Yeah. Okay. Aren't you warm? A jacket, hat, everything? You need gloves. Gloves will be complete. Okay. So, what goes here? If I want to graph? Well, really what I'm saying here is that this thing is going to be equal to, like this thing is going to be equal to minus 3.4, right? And this guy up here is going to be equal to, we're saying 1.4? In approximately, right? Because it goes forever, like she was saying. What would it look like? Can we graph it? Yeah, we can graph it. Do you see really what's kind of interesting here when we factor? If you look at it, what does it mean? We broke down this factor. And what are these? These are really like two lines. The multiplication of two lines will multiply up to that curve. That's pretty cool. You ask me. Okay, so let's go back. And now I want to erase. So let's go. Let me just erase this because we have a good idea. And you guys are expert at square roots, roots of any power, and roots. So, what's it look like? Well, as usual, we have the y and the x, and we have the important points already. One is the y-intercept. When x is 0, y is what? Minus 5. 1, 2, 3, 4, 5. Yes? Well, that's okay. But when y is 0, x is equal to 1.4. So let's say something about right here. And also when y is equal to minus 3.4. Something about right here, right? So this thing must look like, it has to come through here. It has to go through this line. At some point it's going to turn up and go like that. Can you do that? On a final. Okay, so it's not that bad, is it? What did I do? It was not nice. It couldn't be a trick. I had to complete the square. Okay? Now, let's go one more step more difficult. Now, I'm going to put something that's, it has something other than a 1 here. This is a 1 in front of this power. It's a little trickier with when there's something in 1. But let's try it. Do you have this written down? Okay. So let me clear it. Okay, here we go. Now, let's go here. Now what do we got? Let's suppose I have something like this. Y equals 3x squared plus 2x minus 3. Okay, now this is the first time you've seen this without anything other than a 1 there. Now, it might be easy to factor, but you would have to have factors of 3 and factors of 3 such that these factors subtract to 2. And I don't think it's there because you have 1 times 3 here, right? And 1 times 3 here. I don't see it, like, it just doesn't work. 3 times 1 is, 3. So 3 minus 3 is going to be 0. It's not going to work. It's not nice. I can give you an example of one that is nice. Let's say, for example, suppose I have this. I'll create it. Let's suppose I have 2x minus 1 times, let's say, x, let's say, plus 2, for example. So I'm building one up. So this would be 2x squared, correct? And this would be plus 4x. And this would be minus x. Okay? And this would finally be minus 2, okay? So suppose I have y equals 2x squared, and this is plus 3x, right, minus 2, okay? So let's do this one instead of that one up there. And I'm going to complete it 2 ways. I'm going to do it 2 ways. One is we know it can be factored because I built it from factors. But the other is complete the square. You think most problems are easily factorable in real life? No, there's usually going to be a problem that doesn't factor out so nicely. Okay? All right, so let's get rid of this guy. We'll just get rid of this guy. Okay, and now I'm going to be working with this guy. So actually don't need any of this now. Let me go here, actually. I'm pretending like I'm starting at this point. Okay, so again, I do my little table over and over. And here I can put a little x guy and a little y guy. And this part back here is still a line. So when x is equal to 0, you should know that y is minus 2. That's our intercept. And because of the fundamental theorem of algebra, how many x-intercepts do we have? The highest power. So we're going to have to set y equal to 0, not just once like we did with a line, but twice. Okay? All right, now. If we do it the easy way, we already know that now. So what it's telling us to do is set y equal to 0. So I have 0 equals 2x squared plus 3x minus 2, yes? And I know that this is factors of 2, or 1 times 2, yeah? And this is also 1 times 2. But, look here. 2 times 2 is what? 4, yes? And 1 times 1 is 1, yes? And if you subtract that, you do get the middle term 3. You see it? So that means that when there's a minus here in the back, you don't care what's in front. It's automatically plus minus. So I'm saying that we can rewrite this as plus and minus. And obviously I'm going to have a 2x here, right? And an x, otherwise I'll never get back my 2x squared. But now I have to use another 2 and a 1, right? So if I put 2 here, let's say, for example, and a 1. Let's see if that's correct. 2x times x is 2x squared, right? And then this is going to be a minus 2x. No, this is going to be, yeah, this is going to be a minus 2x. This is going to be a plus 2x. Let's see. So that's going to be 2x squared. And this is going to be a minus 2x. And this is going to be a plus 2x. That didn't work either. So let's change the order. So let me put this here. And let me put so, okay, and let me put the 2 and a 1. 2x squared. Okay, now we're talking. That's all right. Let me change my signs. Let me put plus, minus. Okay, 2 times that is 2x squared, right? And 2x times that is going to be a positive 4x. You see it? 2 times 2. That's this guy. And this times this is just a minus x, right? Giving me 3x. And finally, this is going to be the minus 2. So it is a factorization. So we found that one way of factoring this is into 2 lines, is calling this 0 is equal to 2x minus 1, right? Times x plus 2, correct? So that means that either 0 is going to be equal to this factor, right? Why? Why does either this have to be equal to 0 or that actually equal to 0? Why? Mathematically, why is it necessarily true that either this factor is equal to 0 or this one equal to 0?
Because something multiplied by something else needs to equal 0.
That's right. So if you have my hand times my hand equals 0, either this hand has to be equal to 0 or this hand has to be equal to 0. It must be. So, or you must have 0 equal to x plus 2. You see? So in this case, we know that one x-intercept is what? Well, it's just going to be minus 2, isn't it? And over here, you know, we're going to add 1, so the x-intercept here is going to be, right, 1/2, true? Yes? So guess what goes here? Well, you can have a minus 2 here, and we can also have over here a half. Okay? So let's graph it. So what would that look like? This is how fast these things are going by. You've got x and y. These are capital Y. My y-intercept, when x is equal to 0, my y-intercept is 2. You see? That's 0, minus 2. My x-intercept, when y is equal to 0, this is minus 2. So this point here will be y minus 2, 0. You see? And this other one's a half. So this is 1. Right? So a half would be about right here. So that's going to be 0, no, that's going to be minus, it's going to be a half, 0. You see that? So when we connect it, it's got to go through the y-intercept through here. At some point, turn around and go up through here. And that will be the graph of y equals 2x squared plus 3x minus 2. Okay? Yes or no? Am I done? No, I'm not done, because I want you to be able to do this by completing the square. This only worked because I happen to construct something that I know can be factored out, right? I built it up, right? I made it that way by design. But supposing that you couldn't find this, or you couldn't figure out, or supposing there are no nice factors, nice, round, plump numbers, then what do? Complete the square. I'll put it like this. complete the square. I like that. Okay, now let me show you how to complete the square, which I've done before just now, just earlier. Except this time I have a number here that's other than 1. Okay? It's 1 degree harder. If you remember, the one I did before was what? It was something like this. Y equals x squared plus 2x minus 3, right? Notice I have a 1 in there in front of the highest power coefficient, yes? It's a little different because I got a 2 there. All right, let me show you how. Hopefully we're going to get the same answers, but we're going to do it by completing the square. So, oops, well, okay. That's one way of erasing it. I wonder if you have like a return. No. I guess not. Well, okay. So what we were graphing was y equals, what was it, 2x squared? Minus, was it plus or minus? What was it? Plus 3x minus 2? Okay. And so we had already constructed a little table, right? For x and y. And we already know when we set x equals 0, that's automatically constant at the back. And we actually did find this. The fundamental theorem of algebra says that there's going to be 2 x-intercepts. Right? Why do we care? Because when you do physics problems, you know, when I drop my hat, right? It drops like this, but it doesn't drop that way in time, because in time, as it's falling, time is moving. Time doesn't stay still for anybody, as far as we know. So the way it really falls is like this. Suppose now that this is time. No, this is the height. Yes? But I'm moving in time. So as I drop it, time is moving. So it goes like this, move. You see it as going straight up and down, but that's because we're all moving in time together. But actually in time, it's moving like this. Guess what that is? That's the top part of a parabola. Guess how long it takes to hit. Where it hits, guess what that is? That's an x-intercept. You see the applied part? Okay. So, how do we find now? I'm going to what? I'm going to complete the square. How? I'm going to set y equal to 0. Now, I don't know if you remember, but last time I put the number over here, right? But I'm not going to do that. This time, I'm going to try to get rid of this 2 by forcing it, factoring out a 2. Look what's left in. I have x squared, right? But here, this becomes 3 divided by 2x, right? Minus 1. Sorry, this is going to be minus 1/2. Right? Look what happens when this 2 comes back. What's 2 times x squared? Well, that's 2x squared, yes. But when I have 2 times sitting over by here by the 3, guess what? The 2 divides out. So I'm back to 3x. Yes? And when I take my 2 over here, well, the 2's divide out. Wait a minute. Yeah, the 2 should be a 2, right? So, actually, I don't need to divide by 2 there, do I? I just factored out the 2. Sorry about that. I don't need that, right? Because 2 times minus 1 is minus 2. Okay? Are we okay or not? Everybody understand this? Or? Now, what I'm going to do, because of the simple fact that it's set equal to 0, is I'm going to divide both sides by 2. So guess what I have now? 0 equals x squared plus 3/2 x minus 1. Fascinating? Never in your life have you completed a square before? Has anybody completed a square before in their academic life? No? Then it should be very exciting. You see I'm going to add 1 to both sides, yes? Just like I did before. 1 equals x squared plus 3/2 x. Now, how do I complete a square? What's the next step in completing a square? You divide by 2. Don't multiply by 2. You divide that by 2. Can somebody tell me what 3/2 is divided by 2? What's half of 3/2? What is it? 3/4. How does she get that? Because you can put this over 1. You can whip the second guy, you remember? And flip it. And the second guy's in pain, right? So he hollers and he flips. When he flips, he knocks everything off except for 1 dot. And then you go skiing. Yes? What is that equal to? That is half. So 3/2 is 3/4. I'm sorry. Can't make it any harder. So, you take half of that, it's 3/4, and you add it, and you have to square it. So I'm forcing this problem to be a complete square by saying 3/4 quantity squared. And because I did it there so I don't change the equation, I have to be fair and add it on to the other side too. Too easy. So, on this side here, you know, we can just go ahead and this thing will factor. I'm saying that this thing really, there's a plus sign right here, right? So you duplicate the sign in front. So what do I have? I have plus plus. And I have xx, right? Otherwise I can't get x squared back, right? And obviously I'm going to have a 3/4 times a 3/4 to get back a 3/4 squared. And what is this equal to? Well, what is 2 copies of 3/4? To chain. What's that equal to? That shouldn't be hard to calculate.
9/8.
9/8.
Or 9/16. Sorry.
Yes. So what do I have in here? I have 9/16 plus 1. Yes, that I can write over 1, and I can use the nose. The thing I showed you the very first day. If I ever did. And I use the nose. Right? What's 16 times 1? Well, that's 16. Right? And then 1 times 9, well, that's 9. And then 1 plus 16. So that's equal to, now look at this. This is 2 copies of one of them, isn't it? So I can write this as x plus 3/4, 2 copies. Isn't that neater than writing out like that? I just make 2 copies. Yeah. So, what do I have here? Well, that's 25, isn't it? 16ths. And that's equal to what? 2 copies of? Yeah? Is this true? What am I solving for?
X.
X. And what is x actually? I'm solving for x intercepts. Right? So, the only way to do this is to take the square root. Yes? The square root. Why? Because I got a square here, right? So I want to undo that, so I'm going to take the square root, right? But that's the same as raising it to the 1/2 power, true? And I have to do it over here. And remember that any time you square a square, there are going to be 2 solutions. You remember I showed you an example? Okay, now, this is a half power, right? So this will end up as what? Just x plus 3/4. Now, because this is square root raised to the 1/2 power, and there's just division here, no addition, we can write that as plus minus the square root of 25 divided by the square root of 16. We can. But that's 5 squared raised to the half. We know what that is, right? Now, allow me to write the x over on this side so that I'm going to write it over here. I'm going to put the x plus 3/4 here, you see? And over here I'm going to write this as plus and minus the square root of 25 is 5. And the square root of 16 is 4. Yes or no? Yeah. I'm still trying to get x by itself, right? So I'm going to subtract 3/4 from both sides. Do you see it? So x is equal to minus 3, right? And it has a common denominator of 4, doesn't it? Somebody say yeah.
Yes.
Plus and minus 5. So let's see what one solution is going to be. It's going to be equal to minus 3 plus 5 over 4. Guess what that equals to?
Half.
A half. And the other one's going to be x equals, these are intercepts. What is the other one's going to be? Equal to minus 3 minus 5 over 4. That's equal to minus 8 divided by 4. What's that? Minus what? This is a 4. Minus 2. Now, isn't that what we had before for x-intercepts? We did. We had this one was a half, and one was minus 2. Did we do a graph of it? I think we did one before. But so we have capital X and capital Y. When x is equal to 0, y was minus 2. So x is 0, comma, minus 2. And then over here we have a half. So we have, if that's 1, we have a half. So that's going to be equal to 1/2, comma, 0. And then over here, that's going to be equal to a minus 2. So this is going to be a minus 2, comma, 0, yes? And if I connect my points, I know that it has to come through here and go through the y-intercept, and at some point it has to turn back up to go through that next. Any questions?
So, when you have the plus on the end, like in that little red and green equation,
Here?
yeah,
Yeah.
and you say you duplicate the one in front. So if the one in front is a minus, then are they both minus?
Mm-hmm.
Okay.
But if there's a minus in the back, you don't care what's in front. It's automatically minus plus, or plus minus.
Okay.
That's tricks of factoring, but the reason we divide this by 2, because when you add these two, you get back to the middle term, right? 3/4 plus another 3/4 is going to be 3/2. That's why we do it. Are you okay with this? Really? Yeah? That's very good. You must have had a nice dinner or something. What happened? No? Are you going some sort of a buying? Let's see. You're more awake than usual. Okay, so now, I'm going to show you something now. In the most general case, the most general cases are a little harder because I'm not going to have actual numbers. I'm going to have letters. And I'm going to come up with equations that you can use always for any problem like this. Okay? So see if you can follow through. Here we go. So I'm going to get rid of this. Actually, I want the same problem. So actually, I'm going to start. So this is called more general, right? If I have this, look, I'm going to call this A instead of a number. Remember it was 2 before?
Mm-hmm.
And I'm going to call this guy B. And I'm going to call the number C as that thing there, like the last number with no letter, no verb. You see, this is a general case of a parabola. We can keep increasing this. We can go like this. Y equals, let's say, ax to the third power plus bx to the second power plus cx plus d. This is also a polynomial of the form of this, right? Guess how many x-intercepts we have? Huh? 3. That's the highest power. So I expect that it's going to look something like this. It's going to go up 3 times. Bang, bang, bang. Whereas the parabola has 2. You understand? That's pretty cool. But anyway, I'm just saying there's no end to how many polynomials we can keep going up. Right now, I'm going to show you for an equation that will solve all problems that are up to the second power. Let me show you how to do that. Guess how I'm going to solve it? Anybody know?
Imagine.
Well, I think some primitive people, that learned how to start fires, have thought about it as magic. But it's actually math. Math is definitely not magic. Although for me it's a magic tool. How did I solve the problems before? Given that they don't factor easy.
You would complete the square.
Complete the square, da-da-da. Somebody got it. So, even if I did my little chart here without numbers, look at this. Look at this. I put a little x and I put a little y. I can still put x equals 0. Can somebody tell me what y is? C. Yes? Because that's 0, 0. Yes? This is still my y-intercept. Fundamental theorem of calculus say I'm going to have 2 x-intercepts, so I'm going to have to set y equal to 0 twice. And I have to look for these things. Yes? This is how we completed this square. Yes or no? Okay. So, obviously I have to set y equal to 0 when I'm looking for my x-intercepts, right? Are you with me? Okay, but what did I say? For the square to work, we have to have a 1 here, not an a. So I'm going to factor an a out. I'm going to force factor an a out. I'm going to put a here, right? And this is going to be x squared, but this is going to be b over a x plus c over a. Can you see that? Because if I bring that in, guess what? That's a squared. I bring the a over here, it divides out with the a. And I go over here, that divides out with the a, and I'm back to where I was. Now, you remember what I did last time when I pulled the number out? It was probably too much information. I ended up dividing both sides by a to get rid of it. So now what do I have? I have 0 equals x squared plus b over a x plus c over a. Okay? Notice I have a 1 here now. Is this cool? Really cool. What did I do? I took this term over here. Does anybody remember that? I took this term over here. So if I subtract minus c over a, I have x squared plus b over a x. Yes? And what's the rule for completing the square? I I take what? Divide by 2? The middle number, which is? In this case? B over A. B over A is the number I have to divide by 2. If you divide that by 2, in fact, you're doing this. You're taking B over 2A. And that part has to be squared. But because I've added this term, I have to have, right, a B over 2A quantity squared here too. Are you okay with this so far? It's just algebra. Let's take a look at this side here. This is 2 copies of this, right? 2 copies of B squared. So that's B squared, right? Over 2 copies of 2 over 2 copies of A squared. That's what that means. 2 copies of B over 2A. That's 4A squared, yes? Minus C over A, right? And this, by design, remember we have a plus here, so you duplicate the sign in front. Guess what I have? I have plus plus. Yes? And obviously I have to have an x and an x, true? But in order to get a BA squared, I have to have a B over 2A here times a B over 2A here. Now that looks weird, but it works because, let's try it out, just to prove it. Look at this. What's x times x? Well, that's going to be an x squared, right? And what about this? Well, that's going to be a plus a B over 2A x. Yeah? And this is going to be another plus B over 2A x, right? And this last part is going to be the 2 of those guys squared. Now, have you ever seen anything more beautiful than this? Because look what happens. Guess what? B over 2A plus B over 2A. There are 2 of them. Yes? But they're divided by a common denominator of 2. So guess what? You get back to just B over A. You got that? That's pretty good. Now, I'm going to put this over on that side. So I got 2 copies of this, yes? So I got 2 copies of this side that I'm going to put here. Look. X plus B over 2A. Yes? Squared. I have 2 copies of them. On this side, let's take a look at this guy and see what we can do. What I'd like to do is get a common denominator, yeah? This needs another A to be an A squared. And it needs a 4, doesn't it? So I can say that I can rewrite this part here. Look, the B squared over, and I'm going to have this over 4A squared, right? Minus, I'm going to have this A times another A, so I have A squared, but then I have to put an A up here, you see? And here's my C. You see my C? But I need a 4 here, and I have to have a 4 here. Do you see? Now I have a common denominator, don't I? Somebody say I do. A 4A squared, do you see it? And over here I have B squared minus 4AC. I just changed the order of the A to C. Yes? Well, that's what this side's equal to. B squared minus 4AC all over 4A squared. True? Okay. So guess what I'm going to do? Yeah, you got it. The square root of this, because I'm trying to get x by itself. So I'm going to take the square root of this side and the square root of this side, knowing that when you take the square root of square, it's going to be plus minus. Are we okay with this? Mm-hmm. So these are 2 copies. Remember, this is raised to the half power. A half power times 2 is just 1, right? So this side becomes x plus b over 2a. Equals to, now we can put this as the square root over this, b squared minus 4ac, you see it? Divided by the square root of 4a squared, plus and minus. Okay, so now I'm going to take x, I want x by itself, yes? So I'm going to subtract this. Do you see this whole thing, this b over 2a? So I'm going to have x-intercepts are going to be equal to minus b over 2a plus and minus the square root of of what? B squared minus 4ac. You see that? All over, the square root of 4 is 2a. So you see I have a common denominator? So the famous equation for finding x-intercepts for any problem that's raised to the second power is this quadratic equation that you've seen sometime in your life. That's minus plus and minus the square root of b squared minus 4ac divided by 2a. This will always find problems, even if you don't know how to factor it. Now the question is, can you extend this out to a third and see if you can come up with an equation? I think you can, but after that, the fourth, fifth power, there is no more equation that you can simplify it to. I think there's a third power, you can try it, set it equals 0. Anyhow, this is the famous quadratic equation. What is it for? Find x-intercepts. Does it work? Okay. What happened with our last problem? Our last problem was what? Y equals, do you remember 2x?
Mm-hmm.
Right? Plus, what was it? 3x? Was it like this?
Yeah.
Okay, so what is a here? Remember y is equal to ax squared plus bx plus c, yes?
Mm-hmm.
What is a equal to here? In this problem? 2. What is b equal to?
3.
Yeah. And what is c equal to? Minus 2. You see it? So, I can put it in. The x-intercepts will be equal to minus b, which is minus 3, right? Plus and minus b squared, right, which is 9, minus 4 times a is 2, right? And c is minus 2, so this is going to be times minus 4. Right? All over 2, and a is equal to 2, correct?
Mm-hmm.
So my x-intercept going this way is going to be equal to minus 3 plus and minus. Well, guess what this is? This is 16, right? So that's 25, isn't it? So let me say it is.
Mm-hmm.
And that's all over 4, right? Okay, so what do I have? I have two solutions. I have x-intercept equals minus 3 plus 5 over 4. Yes? So guess what that's going to end up equaling? 1/2. You see that?
Mm-hmm.
Or I'm going to have the other solution, x equals minus 3 minus 5 over 4, right? Which is going to be equal to minus 2. So that should kind of help you tie it together, where this equation ever came from. It came from what? Completing the square of a general equation, second degree polynomial. Is that cool or what? Is that, you got kind of a good feeling for that? What's required here? Some algebra is required, right? Because you have to know how to use square roots, right? You have to know how to factor by completing the square, making it work. You have to know how to graph, because in the end, you know what this answer is right here? In a general form, this one's equal to minus b, right? Minus b plus the square root of b squared minus 4ac over 2a, yes? And this guy's going to be equal to minus b minus the square root of b squared minus 4ac all over 2a. That's this guy. Those are your two x-intercepts. Now tell me that's not thrilling. That's like, wow. You ever seen it derived like that? It's really kind of common as far as that's concerned.
So how would you graph that?
Well, if you wanted to graph it, you're only graphing it like, you know, like just, it would look something, I mean, since we don't have actual numbers, I mean, it would look something in the neighborhood of whatever way, it depends how you want to look at it, but in general, let's say I can do this guy. So, what would it look like? It would look like this. We done with this? It would look like this. Something like this. Of course, we don't know exactly because we don't have the actual numbers. But you could look at it like this, maybe. I mean, in a way. You could say that there's some, you know, intercept here, right? And you could say at some point it's going to go up like this, like a parabola, and this x-intercept will be equal to minus b plus and minus, oops, not plus and minus, but just plus, right? B squared minus 4ac over 2a, and this guy would be equal to an x-intercept. In this case, it would be minus b squared minus 4ac over 2a, just in general. And what is this guy going to be equal to? Remember, that's when we had 0, comma c. That's the y-intercept. I can't do a specific one because I don't have any numbers, but generally this is what you're always looking for. You recall when we did the line, which is to the 1 power, it still works, because the fundamental theory of algebra says the number of x-intercepts is equal to the highest power. In case of something other than like a zero slope, they will have, you know, y-intercept. Oh, even a zero slope. Any questions on that? Is it too much for you? Perfect. Is it thrilling? Or is it just me? We'll do that on the final? Maybe. All right. Well, I mean, you have homeworks that are factoring. Okay. The reason I'm doing this is I'm trying to give you a feel, because most of the times you're going to take a math class, an algebra class. They're going to give you exercise and factoring, right? But very few times have I actually realized, you know, the students even know why we're factoring. I'm trying to show you that it has a physical point, right? If something is falling, it falls, and this is time, it falls parabolically. In physics, we don't know what it means to be measured in negative time, but we can figure out when the hat hits. Because in time, we dropped it from here, but in time it fell. This was a phenomenon too, because it was until Galileo discovered that things fall parabolically in a gravitational field. They didn't know that, they thought it just fell, but if you look at things in time is steeper as gravity goes, because acceleration is increasing. You see that? So it has implications in physics, in chemistry, in business, because you have a supply and demand curves. They too can be parabolic. Remember? Not only can you find an x-intercept here, you can set the two equal to each other to find where the two parabolic curves meet, just like we did when there were two lines. That's some cool stuff. I had wished when I first learned it, somebody would have shown it to me this way, because I didn't know what the hell we were doing or what we're doing. We were doing a bunch of exercises for hell of it. Any questions? Now, you realize the class goes on if you want. If any of you decide you want to do it, you can always do homework here, and I can help. But I know that's, I've never seen anybody actually do that. But I think that's a rare event here in this school. But anyway, we gotta get homework done. I suggest if you're not doing it, do it now.
So,
After class. I mean, it's not, class is a lab time. So,
are we doing homework through the end of the book or through the end of the material that we cover?
the material.
Okay.
Yeah. If you can get up to the quadratic equation, I said you're okay.